Welcome to today's topic on formal reasoning for software. In this topic, we'll be covering model checking, managing complexity, and understanding how this all connects to model verification. Here is a nice flowchart I borrowed from 5 principles that define formal verification, which provides us insight into how model checking is an important subtopic of formal reasoning. Before I start going into the details, I wanted to share a very cool word cloud I found from Stanford CS357 course lecture on formal reasoning. I think this word cloud does an excellent job of showcasing all the keywords surrounding model reasoning, model verification, and model checking. It is no surprise that logic, analysis, and verification are some of the most important keywords in this word cloud, as they are strong requirements for any programming task. You can look into this more carefully to find some very interesting keywords that we use every day while programming without realizing that we're using them. Now let us dive into formal reasoning. What is formal reasoning? Formal reasoning is the process of having a precise framework to help us analyze the system's behavior. It is essential for ensuring correctness and reliability, especially for complex systems. It usually leverages mathematical logic in formal languages, which allows us to do more concrete analysis of a system. This, in turn, enables the development of automated tools, also known as model checkers, for efficient system validation. Model checking is a process that focuses on applying formal reasoning to automatically verify system models against desired specifications. We'll be going into more detail on this in the later slides. Now that we have a basic understanding of what formal reasoning is, I would like you to pause and think about why systems would need formal reasoning. Please choose from one of the 3 options provided below. While there is no wrong answer here, the accurate answer is reliability. A system is supposed to behave the way it's intended to ensure that it is reliable throughout its life cycle. It is important for us to remember why formal reasoning matters. We're modeling the software as a finite state controlled system. This allows us to analyze the behavior of the system using formal reasoning, where each state represents a change or transition in the system. A simpler way to imagine this can be to create a graph like structure of states and study the transition between those states to have a better idea of what a system looks like. I've included some examples here to help relate to real world scenarios. For example, a traffic light system is supposed to behave correctly throughout its life cycle. Otherwise, it may lead to unforeseen circumstances. Hence, formal reasoning allows us to detect subtle errors that might be missed by testing. There are 2 common methods for formal reasoning, specifically for model checking purposes: linear time logic and computation tree logic. Linear time logic focuses on a single possible execution path. Meanwhile, branching or computation time logic considers all possible execution paths. Linear time logic verifies the different properties of the system along a single linear sequence of states. Computation tree logic, on the other hand, verifies the properties across the entire tree of the potential future states that the system may have. Linear time logic is always suitable for expressing properties like always, eventually, and next. Computation tree logic, on the other hand, allows for expressing properties about the possibility of future events. Here are some examples which provide us a better understanding on how these reasoning methods would behave. Finally, linear time logic is highly useful in scenarios and systems where the order of events is strictly defined. Computation tree logic, on the other hand, is very useful for analyzing systems with non-deterministic behavior. To recap, LTL or linear time logic is more useful for a single path, which makes it a strong tool for sequential systems. Meanwhile, CTL or computation tree logic is more useful for verifying properties across all possible paths and hence is a powerful tool for complex concurrent based systems. Let us now talk about managing complexity, an integral part of model checking. Managing complexity can be better understood using the following techniques. Technique 1 is abstraction, the idea of making big models smaller and more manageable. Technique 2 is partial order reduction, the idea of checking only what matters in the system. Technique 3 is symbolic model checking, that is, using symbols to check many things at once. Technique 4 is abstraction refinement, whose goal is to find the right level of detail. And finally, we have data abstraction, whose goal is to reduce the data complexity. We'll be going over these techniques one by one and understanding how they help manage complexity, which is a critical part of model checking. As we know by now, abstraction is the simple idea of simplifying complex models by hiding unimportant details. They are particularly important for real world systems, which can be massive and complex systems. It is the idea of creating smaller and simpler versions of models by hiding the right details. Partial order reduction is the idea where we avoid checking the same thing multiple times in a system with parallel parts. We want to avoid checking every possible order. This allows us to save time. It is important, however, to remember that we will still be checking all the different outcomes of the system. Symbolic model checking is the process of using special symbols in order to represent and check many states of a system at the same time. We can represent large groups of states as symbols. This allows us to check each possibility without checking each one separately. Such a method is very efficient for large systems. Abstraction refinement is the process of starting with a basic model and adding more details only when necessary. The main goal here is to start with a very simple model to ensure we can check quickly. It emphasizes on adding more details to the model, which makes it easy to understand the system. Overall, it is about finding the right balance between speed and accuracy of the system. Data abstraction, not the same as abstraction, focuses on how data is represented and manipulated within a simplified model. It allows us to categorize the different database states of the system, which makes it easy to check those. This results in overall speed improvement for the system verification process. For example, it would be checking if the temperature of a subsystem is too hot. To provide a real system example, I wanted to share this pie chart from formal reasoning in computer science. This pie chart does a good job of representing the different formal techniques that we used to improve smart contracts. Smart contracts are a digital agreement stored and executed on a blockchain network. To recap everything we have learned thus far, Formal reasoning and verification is the process of ensuring reliable systems through controlled complexity. Model checking aids in achieving this goal as it provides an automated, exhaustive analysis of system models. Moreover, the key to scalable verification is managing complexity, as real world systems demand techniques to handle the state space explosion. The techniques we learned within model checking and managing complexity assist in formal reasoning and formal verification. I wanted to share a famous quote that seemed relevant to our current topic. I'm sure we've all heard of the famous Dijkstra's algorithm. This Dijkstra quote states that simplicity is a prerequisite for reliability. This means that for a system to be reliable, it must first be simple, as complexity can lead to errors and unreliability. With that, I wanted to say that I appreciate you coming to my presentation on formal reasoning, model checking, managing complexity, and formal verification. Thank you for listening.